In this section, we'll talk about the law of cosines and specifically side-angle-side triangles. Before we move on to the law of cosines, let's review what we know so far. First, for right triangles, solving involves using the ratios where the sine of some angle is equal to the side opposite that angle over the hypotenuse, or the cosine of an angle is equal to the side adjacent that angle divided by the hypotenuse, or the tangent of an angle is equal to the side opposite the angle divided by the side adjacent the angle. Second, for angle, angle, side, angle, and side angle triangles, those can be solved by using the law of sines, where the sine of an angle, in this case alpha, divided by the side across from it, is equal to the sine of beta divided by the side across from it, and that's equal to the sine of the third angle, in this case gamma, divided by the side across from it. That leaves us with two final triangles to solve, the side angle side and side triangles. So what should we do when faced with such a triangle? Well, using what we know about right triangles and the Pythagorean theorem, we can derive the law of cosines, which will allow us to solve these types of triangles. We'll begin by creating two right triangles by dropping a perpendicular segment from any of the angles to the side opposite it. In this case, we're going to start with angle beta and side B. This perpendicular is called the altitude, and we can call it H. So I'm going to label that H. Side B is now divided into two parts. We can go ahead and give those two parts names. Let's call the part on the left X, and we'll call the part on the right B minus X. Notice that if I take X and I add it to B minus X, then that gets us the side B. So the sum of those two sides still makes up the full side of B. Why did I break them up like that? Because I want to look at the two independent right triangles on their own. Okay, now using right triangle relationships and the Pythagorean theorem, here's what we can write. We're going to start by looking at this right triangle that is on the left of the triangle. And using the Pythagorean theorem, we can say that x to the second power plus h to the second power is equal to c to the second power. That's just using the Pythagorean theorem. Now I'm going to look at the triangle on the right triangle that is on the right-hand side. And I'm going to use the Pythagorean theorem again, this time, however, to say that b minus x squared plus h squared is equal to the hypotenuse squared, or a squared. And I'm going to simplify that equation by actually multiplying out b minus x times b minus x, adding h to the second power to it, and setting that equal to a squared. Multiplying b minus x times b minus x gives us b squared minus bx minus bx plus x squared plus h squared equals a squared. All right, now you may be wondering, why in the world is she doing this? Yes, you can do this, but why am I doing it? What I'm hoping to derive is a formula that allows us to solve for this triangle alpha, beta, gamma that is not a right triangle and therefore is not dependent on anything but sides A, B, and C. And I'm using the two right triangles in an attempt to do that. So let me show you what I can do next. Notice that in the Pythagorean theorem that dealt with the triangle on the right, that when I multiplied all this out, I was left with this x squared plus h squared on the inside. That should look familiar to you. Notice that when I worked with the triangle on the left, I also had an x squared plus h squared, and that equaled c squared. So I am going to substitute c squared in the place of that x squared plus h squared. And I'm going to simplify even a little bit more. I'm going to drop the b squared down. I'm going to go ahead and combine these two like terms. So minus 2bx plus c squared equals a squared. All right, so I almost have a formula that only deals with a, b, and c. The only thing that this formula still has is this variable of x in it, and that variable x was part of just one of the right triangles. So I need to express that x in some other way. And here is the way that I'm going to do that. That x is part of the right triangle. And in that right triangle, notice that the cosine of alpha would equal x over the hypotenuse of c. What that tells me, if I multiply both sides by c, is that another way to write x is that x is equal to c times the cosine of alpha. Now, how does that help me? I'm going to take this value of x, and I'm going to substitute all of that in here for x. So I end up getting, I'm just going to write this all out, b squared minus 2 times b, and I'm going to substitute c times the cosine of alpha plus c squared equals a squared. And I can simplify, maybe I can just rearrange a few things here. Let me start with the a squared. Let's just rewrite this so that it says a squared. And I'm going to say a squared is equal to b squared plus c squared minus 2 times b times c, 2 times b times c, times the cosine of alpha. And what I have just created is a new formula called the law of cosines that allows me to solve for any of the three sides of a triangle or the three angles where we are not dependent on a right triangle. We have side A, side B, side C. Those are not part of a right triangle. We have alpha that doesn't have to be part of a right triangle. Notice in this law of cosines that whatever side we start with, in this case A, that the angle that's associated with it on the end is the angle that's across from it. Now, we could have used any of the angles that we began with to drop that perpendicular. We started with angle beta and side B across from it. If I had done the exact same thing but used alpha and A or gamma and C, I simply would have gotten a variation of this law of cosines where instead of starting with a squared, maybe I had started with b squared, or maybe I had started with c squared. On the next slide, let's generalize this formula. Here's what the law of cosines says in words. The square of any side of a triangle is equal to the sum of the squares of the other two sides minus twice the product of those two sides and the cosine of the included angle. For a triangle where alpha, beta, and gamma represent the angles and lowercase a, b, and c represent the sides opposite those angles, we can say if we're starting with a squared, then that's going to equal b squared plus c squared minus 2 times b times c times the cosine of alpha. We know that it's the cosine of alpha because angle alpha is across from side A. If we're starting with b to the second power, then that's going to equal a squared plus c squared minus 2 times a times c times the cosine of beta. Notice that angle beta is opposite side B. And finally, if we start with c squared, that's going to equal a squared plus b squared minus 2 times a times b times the cosine of gamma. Gamma is the angle that's across from side C. Now, this is the law of cosines that I think you should commit to memory. But the variation would be that instead of solving for the sides, a squared, b squared, c squared, if you wanted to solve for the angles, alpha, beta, and gamma, you would simply solve each one of these equations for cosine of alpha, cosine of beta, or cosine of gamma. So here is what that might look like. If I wanted to isolate the cosine of alpha, then what I would do is I would subtract b squared, I would subtract c squared, and then I would divide by negative 2bc. So that would look like this. I would say a to the second power minus b to the second power minus c to the second power. And let me just say that would equal negative 2bc times the cosine of alpha. To get that cosine of alpha by itself, all that I would have to do is divide by negative 2bc and divide by negative 2bc. And that would get me a formula for the cosine of alpha. I could do that same procedure for each one of the other angles. And that generalized formula would look like this. Notice that when, let's just look at the first example, when they solved for the cosine of alpha, the first formula here is the one that we did, the a squared minus b squared minus c squared, all divided by negative 2bc, right? That's what we wrote here to solve. The variation of that is simply factoring out a negative 1. Notice that we had a positive a squared, that turns into a negative a squared. We had a minus b squared, that turns into a positive. We had a minus c squared, that turns into a positive. And then because of that, the denominator also switches. So you can use either one of these formulas. You will typically see me always just remembering the basic form of the law of cosines, which is the one that starts with a squared or b squared or c squared. Now let's look at an example. Solve the triangle with alpha equal to 30 degrees, b equal to 3, and c equal to 4. Round to the nearest tenth. Okay, so I have been given an angle of 30 degrees. I've been given a side b equal to 3 and another side c equal to 4. So I've been given, if I follow these in order, a side, then an angle, and then a side. So that is a side angle side triangle. And in looking in this, I see that I do not have an anchor. Right? I know the 30 degrees, but I don't know the side across from it, and I don't know either of the other two angles. So I cannot use the law of sines, and however, I can use the law of cosines. So I'm going to go and start with, let's see, I know two sides, so I'm going to try and find side A. So I'm going to set up the equation a to the second power equals the other two sides are 3 and 4, so that's going to equal 3 squared plus 4 squared minus 2 times 3 times 4 times the cosine of the angle that's across from A. The angle that's across from A was 30 degrees, so that's going to be the cosine of 30 degrees. Here is what the law of cosines actually says, in case you needed it. But you'll see that if you just think of it in terms of, okay, I'm starting with the side, that's going to equal the sum of the square of the other two sides minus 2 times those other two sides times the cosine of the angle that's across from where I started with. Yes, I guess you might say it's memorizing it, but it's more like it's just making sense. You're committing it to memory. So now I'm going to substitute into my calculator everything that's on the right-hand side. And when I did that, I got that a to the second power is equal to 4.215390309. And then when I square root that, I got that a was approximately, I think it ended up being like 2.05, but if I'm rounding that to the nearest tenth, that would be 2.1. Now, I've talked about this before, but it's worth mentioning again here. I'm going to say that a is equal to 2.1, but if I need to use that 2.1 value in any further computations, I'm actually going to use that 2.05 and whatever else was following it. I'm going to use the exact number in my computations. Okay, so now you may have noticed that I do have an anchor, don't I? I've got the 30 degrees, and now I know the 2.1. Could I use the law of sines? Yes, I could use the law of sines at this point. The only reason I'm going to choose not to is because you might recall when you use the law of sines that there is a possibility of the ambiguous case, meaning that when you do inverse sine, you get an angle measure, but then you have to check to see, could there be another angle measure? Could there be another triangle? And if the answer is yes, there could be, then you're in a quandary of, well, which should I use? Which angle should I use? And you can determine which one to use if you look at the sort of the values of the angles in relationship to the sides, right? And we know that the smallest angle should be across from the smallest side. To avoid all of that, what I would recommend is just sticking with the law of cosines. It may feel like it's a little bit more to write down, but our calculator is really going to do the hard work. Okay, so here is what I would probably do next. I would move over to let's say gamma. Let's take a look at gamma. So if I want to solve for gamma, then I'm going to start that off with the side across from it. So if I want to solve for gamma, then I'm going to start with the side across from it. And here's what I'm going to write. I'm going to say that 4 to the second power is equal to that 3 to the second power, and then that 2.1 to the second power, which again, I'm not going to put 2.1 on my calculator. I'm going to put the full number in there, minus 2 times 3 times 2.1 times the cosine of gamma. Now, if I isolate that gamma, then I'm going to get that the cosine of gamma is equal to 4 to the second minus 3 to the second minus 2.1 to the second all over negative 2 times 3 times 2.1. Now, I'm going to put all of that into my calculator, and when I do that, let's see, I got that the cosine of gamma was approximately equal to negative 0.22. And when I do inverse cosine of each side, I got that gamma was approximately equal to 103.1 degrees. 103.1 degrees. Let me write that in. 103.1 degrees. So I'm almost there, aren't I? I've solved for A, side A. I just solved for gamma. And the only thing left is beta. And beta won't be bad at all because beta is simply the third angle in that triangle. So I'm going to take my 180 degrees. I'm going to subtract out the 30 degrees. I'm going to subtract out the 103.1 degrees. Again, I'm going to use the actual number, not the rounded answer. And I find out that angle beta is approximately 46.9 degrees. So 46.9 degrees. So, moral of this story is that stick with the law of cosines if you can. If you really want to use the law of sines, you can, but just be careful because it's not just the angle that the calculator gives you. There could also be that ambiguous case of that other possible angle measure.